So we were working on section 9.4, and we talked about this, but I thought it might be helpful to just look at this again real quick to remind us what we were talking about. So we had this equation where nitrogen is reacting with hydrogen, and we had this illustration, and we saw that in this little lasso, there's the ingredients needed to make two ammonia molecules, and here we can make two, and here we can make two, and then we have some nitrogen that gets left over because there's no hydrogen for it to react with, and so it just gets left sitting there. Just like when you're making sandwiches and you don't use up all the bread just sits there, right? So we said that the limiting reactant is the one that runs out first, and it limits how much you can make. So in that example, hydrogen was the limiting reactant. So how do we figure out which one's limiting? Well, we have to correctly calculate the amounts of products that would be formed. So it's the same process we did with the sandwiches. We took the amount of bread we had and we figured out, well, how many sandwiches can we make? And we took the meat, how many sandwiches? We took the cheese, how many sandwiches? And then whichever one gives the least product, the smallest amount of product, that's the one that limits the reaction. So let's look at this methane and water reacting to form products of hydrogen and carbon monoxide. It's a balanced chemical equation. And here's our illustration of what happens. So if we had 5 methane molecules and 3 water molecules, what would happen? Well, 1 methane reacts with 1 water. Forgot what that was. Mickey Mouse upside down. And forms the products. And here this one and this one could react to form, and these two could react. And what's left? Well, we've got methane left over. We have all the water being used up. Water is the limiting reactant. Water's the one that gets used up first, and that is the limiting reactant. So this is the more conceptual concept behind these calculations that we're going to do. So in that example, the amount of product was limited by the water, the amount of water. We say that water is the limiting reactant and that methane is in excess. There was extra, right? Extra, excess. So these are the steps that we're going to do for solving these problems involving limiting reactants. First we need a balanced chemical equation. On an exam, I'll give that to you. In the homework, sometimes they make you write it out and balance it. And you're like, why do we have to do that? Well, because you need to know how to do that. And so if you already learned, then it's a refresh. It's, review. If you didn't learn it, it's kind of a kick in the pants saying, hey, you still need to learn this. So you start with the balanced chemical equation. Then you calculate the mass of product that can be formed from each reactant. You choose the smaller mass of product, and you look back at which reactant gave you the smaller mass, and that's your limiting reactant. So those are the steps. Let's do some examples. So here you react 10 grams of A with 10 grams of B. What mass of product will be produced? And they're giving us the molar masses because these are made-up substances. So we're going to use the balanced chemical equation to help us organize this information. So it says we have 10 grams of A. So under A, I'm going to write 10.0 grams. And it says we have 10 grams of B. So I'm going to write that under B. And it's asking what mass of product. Well, there's only one product. It's C. So we put the question mark there. And it says what mass. And so that's going to be grams. Now, what's different about this than the previous stoichiometry problems we did? There's 2 masses, right? Before, we just had 1 mass, and we calculated 1 mass. Here we've got 2 masses. So that's how you recognize that this is a limiting reactant problem. They give you 2 masses, and then you have to do 2 calculations. So we're still going to have our same path grams to moles to grams. Grams to moles to moles to grams. We should make up a song. We could make a video. Be awesome. Somebody probably already did. I don't have time to look for it. Okay, so we're going to start with, we're going to have two of these. Let's start with A just because it's first. So we're going to start with 10 grams of A, and then we're going to have 3 fractions. And what goes on those fractions? Well, it's our path, our map. Grams to moles to grams. So grams of A to moles of A to moles of what we're trying to find. What are we finding? We're finding C. Important to remember, where are you going? No, that's not right. I did that to test you. Grams of C. Then we put these units in because we want the grams of A to go away. And we want moles of A to cancel out and go away. And we want moles of C to go away. Dimensional analysis, units tell us what to do. We get all of our units set up and then we stick the numbers in. Okay, unless you really have a firm grasp on this, if you start putting numbers in first, you're going to forget what you're doing. Get it all planned out first and then find the numbers. So what's the relationship between grams of A and moles of A? Well, they gave it to us. It says the mass of A, the molar mass, is 10 grams per mole. So that means for every 1 mole of A, we have 10.0 grams of A. And they gave us the molar mass of C was 25. We need that over here at the end. 25.0 grams of C per 1 mole of C. The molar mass, the term at the beginning and at the end, does not use any numbers from the balanced chemical equation. Do not put the coefficients in there. Yes, it says 2C in the equation. That's fine. We're going to use that 2 in the middle term, but you can only use it once, so don't put a 2 over here. Don't say 2C over there. That's wrong. So first term, last term are molar masses. The middle one comes from the balanced chemical equation. In front of the C is the number 2. And in front of A is an understood 1. 1 mole of A gives 2 moles of C. And so the math on this is going to be fairly simple. 10 divided by 10 times 2 divided by 1 times 25 divided by 1 is going to come out to be 50. 50 grams of C. Any questions? We're going to do the same thing for B. We have 10 grams of B. And we're going to have times in a line, times in a line, times in a line equals grams to moles to moles to grams. Okay, this time we're starting with grams of B, so we go to moles of B. We're still trying to find the mass of C ultimately. So don't switch this up now and go to moles of A or something crazy like that. We're basically, you know, if we go back to the Dora analogy, okay, so Dora is starting at point A and Boots is starting at point B, and they're both going to point C, okay? And so they're both going to end up at the same place. So you're starting with a mass of a different compound, but you want to end up with both of these with the mass of the same compound at the end. So this is moles of C and grams of C. Then we put the other units in so they'll cancel out. And we've got it all set up, now we just go looking for numbers. What's the relationship between grams of B and moles of B? Well, it's the molar mass. Because these are made up, they gave it to us. 1 mole is 20 grams. What's the relationship between grams of C and moles of C? Well, it hasn't changed since we did our first equation. It's still 25. Look at this. This term and this term are exactly the same. You see that? They're going to be exactly the same because we're ending up at the same place. The middle term, we get these numbers from the balanced equation. In front of C is a 2, and in front of B is a 3. I don't want to do that in my head. I could, but I'm not feeling well. I'll use that as an excuse. 10, 16, 10 divided by 2 times 2 divided by 3 times 25. I get 8. 8.33. Yeah. Anybody else get 8? Okay. Doing stuff in your head is great, as long as you get the right answer. You know, and my poor 5th grader, he's doing all this stuff, and then he has to check it with long division. He does the problem right, but then he makes a mistake in his long multiplication on the check. And so then he's like, what did I do wrong? But he can't use a calculator. You're not in 5th grade anymore. You get to use a calculator. Go ahead and use the calculator. Okay, so we end up with 2 answers. This problem only has 1 correct answer. How did we choose the answer when we were figuring out how many sandwiches we could make? It's the smallest one. It's the smaller one. Because as we're doing this reaction, we're using up A, we're using up B, we're making C, we're making 6 grams of C and 7 grams and 8 grams, and we get to 8.33 grams, and we run out of B. Reaction stops. Occasionally I'll get students who want to add these 2 numbers together and say that we can make 58.33 grams of C. It's very creative, but very wrong. It's just the smaller number. So think back to the sandwiches if you get confused. What did we do with the sandwiches? We took each ingredient and figured out how many sandwiches we could make. And it wouldn't make sense to add them all up and say that we could make, I don't know how many that would have been, but it would have been a lot of sandwiches. Because that would be ridiculous, right? So that's the smallest. That's the mass of product. Okay? So which of these, this isn't asking you this, but which of these would be the limiting reactant? B. So we take this number and we go back and see which reactant gave it to us, and that's the limiting reactant. Limiting reactant is kind of long to write out, so LR, limiting reactant. So the limiting reactant is B. That's the one that gets used up. There'll be some A left over. And in higher level chemistry classes, you get to calculate how much A is left over, but we don't do that here. We just say some. Any questions?
That's a lot easier than the slide example.
Good. I'm glad that's easier than the slide example. I changed the slides. Okay, this is important. I mentioned it. We cannot add the total moles. Actually, I didn't mention this. We can't add the total moles of all the reactants to decide which reactant mixture makes the most product. Because the masses, each compound has a different mass per mole. And so you can't just look at the number of grams or the number of moles, or there's really no shortcut. There are other ways to solve this problem, this kind of a problem. And I've tried teaching those ways, and this is the one that makes the most sense for most students. It's just the most straightforward. It involves a tiny bit more work, but it's better to do a little more work and get the right answer than get confused in the middle and get the wrong answer. Let's do another example. How many grams of ammonia can be produced from the mixture of 3 grams each of nitrogen and hydrogen by the Haber process? Do we need to know that this is the Haber process for making ammonia? No, we don't. They just threw that in there because, I don't know why. Okay, so, balanced chemical equation. They're asking how many grams, and they're giving us amounts. And so we're going to use this equation to organize this information. 3 grams each of nitrogen and hydrogen. So under nitrogen, I'm going to write 3.00 grams. And under hydrogen, I'm going to write 3.00 grams. And under ammonia, I'm going to write question mark grams. That's your little shorthand that will help you when you start to get lost. And then we remember what's our path. Grams to moles to moles to grams. So the previous one was made up compounds, just A, B, and C. This one's actual elements and compounds. So we have the balanced chemical equation. We're given 2 masses, and that's what clues us in that this is going to be a limiting reactant problem. We need to do 2 equations, one with each mass, to figure out, well, if we use up all the nitrogen, how much ammonia can we make? If we use up all the hydrogen, how much ammonia can we make? So we start with 3.00 grams of nitrogen, and we go with our 3 conversion factors here. Grams of nitrogen to moles of nitrogen to moles of NH3 to grams of NH3. And sometimes we don't anticipate well how much space we need. That's okay. Yeah, okay. I think I learned how to figure this out. Yay! Phew. Okay. My husband helped me with that one. He's my tech guru. Okay, so there we go. Grams to moles to moles to grams, and then we get the rest of the units in here. Moles here and moles here. Can you see why it's important to put the formula for the compound in there? Because we've got 2 kinds of grams, grams of nitrogen and grams of ammonia. And we've got 2 kinds of moles, moles of nitrogen and moles of ammonia. And if you don't put the formula for the compound in there, then it's really easy to get this all mixed up. So I'm going to cancel out my units, and I'm going to stick numbers in here. So the middle one is the easy one. How many moles of nitrogen? Well, there's 1. And for the ammonia, that has 2 in front of it. It's this guy right here. So that just comes down here into our equation. Then we need the molar mass of nitrogen. Well, nitrogen is N2, and each mole of nitrogen atoms weighs 14.01. So this is going to be 28.02 grams of nitrogen. And then for ammonia, we should probably actually calculate that. We're going to have 14.01 plus 3 times 1.008. And that's going to be 17.03 grams, which is equal to 1 mole. So 17.03. So 3 grams divided by 28.02 times 2 times 17.03, and I come up with 3.65. Anybody else get that? I'll try it again. 3 divided by 28.02 times 2 times 17.03. I got it again. Must be right. So if we use up all the nitrogen, that's how much ammonia we can make. Well, that's nice, but we need to do this again. The nice thing is, you've got that all figured out once, and now you have a pattern to follow. We're just going to do it with the hydrogen instead. So 3.00 grams of hydrogen. We're going to go to moles of hydrogen. And then we're going to go, again, Boots and Dora are going to the same place. Both of these are going to grams of ammonia, NH3. Get all your units in first. And cancel them out. The last term is the same. That looks like a 2, doesn't it? It's not a 2. It's a 7. So this is 17.03. Writing on this iPad is harder than you would think. The middle term. Well, ammonia still has a 2 in front of it. What's in front of hydrogen? 3. And then over here we need the molar mass of hydrogen. 2 times 1.008, so 2.016. 3 divided by 2.016 times 2 divided by 3 times 17.03. I think something went wrong. Got 0.17, I don't think that's right. 3 divided by 2.016 times 2 divided by 3 times 17.03. That's better. Okay, so that time I got 16.9. Anybody else get that?
Yes.
Okay. Yeah, do those calculations twice. We're going for 2 the same. So sometimes students get through this successfully and then they're like, now what do I do? Think of the sandwiches. We're running out of one of them. When we make 3.65 grams of ammonia, we have run out of nitrogen. We can't make any more ammonia. It stops. We're choosing the smaller one as our answer. On a lab question or a homework question where you're actually writing this out, you have to specify which of these numbers is your answer or you don't get full credit. You have to pick an answer. And then it doesn't ask, but which reactant is the limiting reactant? Did it again. There we go. See, old dog, learn new tricks. This guy. Nitrogen is the limiting reactant. It's the reactant that gave us the smallest amount of product.
So that question's not clear.
It's not asking which is the limiting reactant on this slide. I just threw that in there as a bonus. Any questions about this problem?